Hello, welcome to online tutorial videos from JCB Labs. For more information and to download the content of this video, you can visit us at www.jcbrolabs.org. In this video, we will learn about the stability analysis in control system. So as we know, the stability is the prime factor or prime requirement in designing any control system. So we will have a brief discussion about that, and then mainly this video will talk about how to create Routh-Hurwitz table from a given transfer function and what exactly is Routh-Hurwitz criteria. So let's start. So in stability, so if we talk about the stability, so stability means the system response. If we talk about the system response of the system, so of the closed loop, it goes about to near to some fixed point, so that as time increases it stops oscillations and it's finally set to some previous design set point. So then we say, okay, our system is stable. So there's several definitions for stability, and one of the famous is the Bibo stability criteria. So Bibo stability means bounded input and bounded output. So we can say bounded input and bounded output. So what exactly means by this bounded input? Bounded input means if the input signal which we are applying to any control system, say this is our transfer function TS, and we are applying here some RS here, and the output this is the CS. So we are applying some bounded input. So bounded input means the amplitude is not going out of certain limits, and these are the within the well defined limits of the system. For say step signal or step signal or your unit step signal, whatever you can say, or bounded input like you are applying some sinusoidal signal. So it is not like it is a simple definition is it is well within the limits, certain limits. It is not like input is going towards the infinity or towards the outside of the input parameters of the controls. For example, take a DC motor. So if the input requirement is 5 volts, so it should not be like you are applying 10 volt to the input signal. So bounded input means you are applying within the limits of that physical system into it, and based on that stability means if we are applying this bounded input, so the output should also be bounded. So bounded output includes like either output goes towards 0 as the time increases like this, or it reaches up to certain value like this, or it goes takes certain oscillation and then limits to something. So then it is this is the bounded output and our system is stable. So there are basically three categories in this, like number first, when we have a unstable system. So based on these analysis, like whether we are applying a bounded input and how our output behaves, like whether it goes through unbounded or some stable or non-stable. So based on that we have three different categories. So one is the unstable system. So what happens in unstable system? Suppose we are taking some bounded input as a step signal, and if we draw in terms of the graph, like this is the time and this is the amplitude of the system, the output of the system. So we have applied some bounded input like this unit step signal for the system, but our response goes like this. Okay, it starts this and keep on increasing this, and as times goes to infinity it keeps on increasing and so on. So our system will say, okay, our system is unstable because we are applying some bounded input but system is keep on increasing, and then our system is unstable system. So a typical example is like an inverted pendulum or the open loop system. So in inverted pendulum, what happens, as soon as you create a slightly disturbance, it goes out of bounds and it don't remain inverted. Similarly, there are several other examples as well. Second system example is the marginally stable system. So in marginally stable system, like what happens, again, suppose we are applying some bounded input. This is time axis and this is the amplitude. So say we are applying some bounded input like this one. This is the input signal and maximum limit is 1. But the output goes like this and keep on increasing. But after st tends to infinity, it remains oscillating but remains within the limits. So the output is within these limits, say 1 plus mu and 1 minus mu. So output remains within these limits. Then we say such system is the marginally stable system. So you can think of like oscillators. So these are the marginally stable system. And a third one is the stable system. The third category is the stable system. So this is the prime requirement in order to make any stable system. So we want to create, let's discuss it a little later. So let's say again this is the T and this is the amplitude, not mode of it, and this is the input signal. So our system can behave in several manners, like our system can go as time t tends to infinity, our system output goes towards 0, or our system can reach up to certain limits or tries to remain up to the set point, or it can have some starting transient oscillation and then it settles down to certain limits. So all these are the output of the system, and all these are the categories of a stable system, like our system is stable. So this kind of analysis of the transfer function of the system is must in order to understand whether our system is going to be stable or unstable. And our prime requirement is to make any unstable system stable by means of feedback control or all those things, or by closed loop control. So when we talk about closed loop, so we have a feedback system. So suppose we have some unstable system h of s here, and then we apply into a feedback path, and this is the RS. And this is the output of this entire system CS. So our main requirement is, like, if this system is unstable, so we want to create a feedback loop so that, or we put some controller. Those are the system designing application, like how to make this system as a stable system. So now a question should arise, like how to find whether a system is stable or not. A system is stable or unstable. So this is the question. So let's say we have some transfer function. Let's say we have some transfer function h of s is given as like 1 divided by s plus 1 and then s plus 2 and then s plus 3. So this is our third order system, and if we want to take the time response, like one category is like if we plot ht, and if ht goes like haywire, then we say okay, this system is unstable. But here it is a third order system. It is a third order transfer function. If we talk about the denominator, then it's to find the this time response of this system, it will be a very critical task. So there are certain techniques by which we can just by looking at this transfer function, we can identify whether this system is a stable system or unstable system. So we are going to do that. So prior to that, there are two things: zeros of the transfer function and poles. So zeros are the points where h of s, or h of suppose any point k, becomes 0, and poles are the points where transfer function, let's say m, becomes an infinity. That means poles are those points where transfer function is not defined. And then we say okay, let's try to find out the transfer function, the poles and zeros of this h of s. So there are no zeros in this transfer function, and there are the poles. There are three poles where this system becomes infinity, like -1, these are -1, -2 and -3. So these poles have a very specific conditions on the stability of the system, and these conditions are like once we got to know these poles of the transfer function, then we create a pole zero plot of this transfer function. So pole zero plot means we try to plot these zeros and poles on a complex plane. So this is a real part and this is the j omega axis. So it is a complex plane, or generally known as the S plane, because we are taking the Laplace transform. And then we try to plot these poles and zeros. So we create zeros by putting a 0 marks, and we create poles by having this -1. So we have poles here, this cross sign here and here. So this is -1, this is -2 and this is -3. Let's say if I have any pole, okay, let's say we have transfer function, let's change a little bit, s plus 5. So we have a pole or a 0 at -5. So we represent 0 by a different symbol, by this 0 sign. So this is the point where our system is becoming 0. So this is the 0 plot, and from this pole 0 plot we can identify the stability of the system. So there are certain rules, like how to find the stability over the rules. So the rule 1 says system is stable if all roots are on the left side of S plane. Left side of S plane. So this left side means the left portion around 0, around this j omega axis, is known as the left side, and this is the right side of S plane. So our system will be stable if all roots lie on the left side of S plane, and if any root is lying, if any root of system transfer function, so whether it is a closed loop transfer function or an open loop transfer function, so that is why we are using a system transfer function, because it could be a closed loop system or open loop system. So if any root of system transfer function lies on right side of S plane, on right side of S plane, then our system is unstable. So okay, well, if any root of the system lies here, then we can say okay, our system is unstable. Now the third point is, what if any root lies on this geometry axis, because that could be the probability. So if any root in a multiplicity of 1, if any root lies on j omega axis, this j omega axis, then our system will be marginally stable. So these are the some of the three basic conditions based on which we can find okay whether our system is stable or not. So let's take an example. If I give you this example, okay, we have a transfer function. This is our closed loop system. This is plus minus. So this is, let's say, R of S input, and it is going into H of S, and this is the C of S, and we have this unity feedback system. So our transfer function, system transfer function, will be this CS by RS, as we know from the definition of this transfer function, output upon input, and this will be HS upon 1 plus HS, right? Then let's say we have been given with HS equals to 1 divided by S plus 1 and S plus 2, and we want to know whether this closed loop system is stable or not, So simple thing is, we need to find, okay, from our understanding what we have learned so far, we can say okay, transfer function of the system is like, it will be 1 divided by, if I'm right, S plus 1, S plus 2 plus 1. So if we talk about an open loop system means when we have this transfer function only. Open loop system is, this is the open loop transfer function. So when we have this transfer function only, this transfer function is stable, because it has both the roots on the left side of S plane, minus 1 and minus 2. But when we apply in the feedback loop, our transfer function of the system change. So we can't be sure whether our final transfer function which is becoming, whether it will be a stable system or not. So let's figure it out. It will become S square plus 3S plus 3. So if we try to find the roots of the system, so this will not be so easy. So there will be some complex root of the system. So if you, let's solve it. This is S square plus 3S, so let's find the root from minus 3 plus minus under root B square minus 4AC divided by 2A. So there will 2 root 3 plus minus 9 root 3I divided by 2. So these will be 2 roots of the system, and we can decompose this system as S plus A and S plus B. So let's say A, where A is equals to minus 3 plus root 3I, and B is equals to minus 3 minus root 3I by 2. Right. So both the roots of the system, if we try to plot this pole zero plot of this system, and then we will find that both the roots are lying on the left side of S-plane. A will be here somewhere and B will be here somewhere, and this is the real axis and this is the j omega axis. So this point will be nearly minus 1.5, and similarly we can easily find this value and this value. So both the roots are lying on the x-axis on the left side of the S-plane, and okay, the system is stable. Now it's good, but the question arises when our system become a little complex. For say like for complex system, so basically in order to find the stability of the system, if we look at it carefully, we don't need to find exactly where our roots are lying. We are only interested whether they are lying on the j omega axis, whether they are lying on the left side of S-plane, or whether they are lying on the right side of the S-plane. So we are not interested in what is the exact value of those roots. We are only interested in which location on this S-plane the roots are lying, or whether there is any root on the right side or not. So if somehow we can identify like whether there is no roots or there are one root or two roots on the S-plane, so without finding the roots location exactly or the values of these roots, we can say okay, whether our system is stable or not. So let's say we have a complex system of some transfer function, because our transfer function could be complex, and this is this Rs, and our system is say for higher order. Here we have tan s plus 2 divided by s into s plus 4 plus s plus 6 plus s plus 8 plus s plus 10, and we want to find whether this closed loop system in a feedback configuration is stable or not. So obviously finding the roots of this system will be a very tedious task, and we can find these roots by we can't find these roots without the help of a computer. So if we go for it, it will become tan into s plus 2 divided by s to the power 5 plus 28 s to the power 4 plus 284 s cube plus 1232 s square plus 1930 s plus 20. So obviously we can find it like we will not be able to find the roots of this system. So that is why, and from our previous discussion we came to know like we are not interested whether what is the location of the roots. So we are only interested where on S-plane these roots are lying. So there is a criteria in order to solve our problem, and that criteria is known as the Routh-Hurwitz criteria. So Routh-Hurwitz in some time back they come up with a method by which, without finding the exact roots of this transfer function, we can say okay, this many of roots are lying on the right side of S-plane and this many of roots are lying on the left side of the S-plane, and from that we can estimate whether our system is becoming stable or unstable. So in order to understand how this Routh-Hurwitz criteria works, so let's take a simple example first. Right. So let's say we have a simple example. So Routh-Hurwitz actually create a table, and based on that we find how our system is going to behave. So let's say we have this system. Here it is Rs, and then we have this 1000, divided by s plus 2, s plus 3, and then s plus 5. So still it is a critical system because at denominator we have a third order system, and then we have this is in a feedback loop. Yep. So now if we try to find the transfer function of this system, that will be Cs by Rs will be equals to 1000 divided by s to the power 3 plus 10s square plus 31s plus 1030. Okay, so this is become our third order system, and this is the closed loop transfer function. So this particular variable or this particular denominator equation, there is another name of this equation as well. This equation is also known as the characteristic equation. Characteristic equation. So the name of this characteristic equation is because just from this equation we can find the several properties of the transfer function. So now as we say, it actually creates a Routh table. So we'll now understand how to create this Routh table. So in order to create Routh table, first we create the coefficient of the highest power of the s component. So highest power is the 3. So this is the odd component, so we'll take 3 and we'll go towards 0. All the odd component from the odd power from the highest power towards 0. So it will be 3 and then 1 and then 0. So s to the power 3 component coefficient is 1, s to the power 1 coefficient is 31. That means first we will create the highest power of s, and then from that highest power we will start writing the odd power component towards 0, right? And then the next highest power, that is the s square, and similar procedure will be applied. From that power will go up to, so first power or even power 2, then 0, so it ends. So it will be 10 and then 1030. So there is a thing, this becomes, in order to solve the computation, so because these two components can be divisible by 10, so instead of writing 10 we'll write 1, and instead of 1030 we can write 103. So this should be noted that if all the values in a row are divisible by some common factor, then we can divide those things. Now we will write the next coefficient. Now we have start from this power, s to the power 3, s to the power 2, and then we will go from all the powers towards the last one to s to the power 0. So in order to, there will be two values here and here, no, only here, and in order to find this, this is very simple. Just follow the thing, multiply this component with this minus this component with this. So it is like finding the determinant of a matrix. So in books or notebooks, if you go through it, so they have taken the negative sign, this minus this, that means minus sign outside, then this component minus this component. But if you are taking directly, we can have, so this component minus this component multiplied with this component minus this component multiplied with this component divided by this component. So ultimately what is happening, it is becoming a smaller matrix. So we are taking the determinant and we are dividing the determinant from the very first component. So that is what exactly we are going to do here. So it will be 1 into 31 minus 1 into 1030 divided by 1, because in our case it is very simple. So this, if we calculate, this value will come out to be minus 72, and the next series can't be calculated because there is no number. Now the next number, so what we are doing here, we are taking this portion outside of it, let's say, so we are taking this calculation somewhere. Okay, it's not. So if you have gone through, let's erase it and then we'll write simple. The value of this was minus 72. Now for calculating this second component, we will have to go to the third values, but these values are 0 0, third component, so it will be 0. Now in order to compute this as 0, again now we will take upper to 1, like this one and this one. So in this we will take as we did earlier, minus 72 into 103 minus 1 into 0 divided by minus 72. So this term will become 0 and minus 72 will be cancelled out, and the value here will be 103 only, and then all other components will be 0. So now let's change it. Let's erase it. I hope you understood. So this component comes out to be 103. Now let's have a look to understand how this Routh table works. We just check the sign of this first column. Remember, we are interested only the signs of this first column. So this sign is positive, then this sign is positive, then is negative, and then it is positive. Okay, so now the rule 1 says how to find whether this system is stable or unstable. So it simply says if there is no negative sign in first column, then our system is stable. So this is the thumb rule. If there is no negative sign in this first column, then it says our system is stable. So obviously opposite of it, that means if there is a negative sign in this first column, then our system will be unstable. Okay, so if there is a sign, then our system is unstable. So just by looking at this table, we can find, okay, this is plus, this is minus, okay, one negative sign is there, our system is unstable. So we can say this system is unstable. Now another thing is we are interested like how many roots are lying on the x-axis. So number of roots, number of right side right plane roots are equal to number of times sign changes. Wait, this is not the negative sign, it is just to indicate the point 2. So if we are interested number of times this sign is changing, that means one times it is going from this positive to negative. So there is one time sign change, then it is changing from negative to positive, second time sign change, the 1 2. So there are two times of sign change. So in this equation 2 times sign is changing. That indicates, that means 2 roots are on right side of S plane. So I hope this have solved your major concern, like how to find the stability if our transfer function goes of higher order. So just by looking on this route table, just by solving this route table, we can find how to change the sign, or how many, whether our system is stable or unstable, or how many roots are lying on the right side of S-plane. So all the information can be found it. So that is why this Routh table or Routh-Hurwitz criteria is most important, and this is also known as the Routh-Hurwitz criteria of the stability. So there should not be any negative sign on the first column on the route table, and then our system will be stable. Now there are several cases. There are two cases in this case: when some component becomes 0, or when there is an entire row is 0. So there are certain categories of the problem and how to solve them. And then there is a stability analysis, like how to design a system in order to make our system is stable with the help of this route table. So we will learn these things in our next class and in our next video. So that's it for this video, and I hope you understand a lot related to the stability and how to create a route table. So that's it for this video. Thank you.